In conclusion, if you have inverse problem ax equal to b where you want to find the unknown x, so we can use the Gauss elimination, but consider your A matrix is constant and remain unchanged. For example, you have a mass spring system that can be represented by matrix A, and since the mass, stiffness, damping are all the same as well as the boundary condition, then your A matrix will not change. If we give an input force to the mass spring system, of course the system will vibrate and generate the output response. For example, at time equal to 1, you have force A1 here that cause the system to vibrate at B1. At time equal to 2, you have force A2 here that cause the system to vibrate in B2. And then if you continue, then you will obtain multiple set of input force and multiple set of output response. For this situation, using the LU decomposition to solve the inverse problem is much more efficient compared to the Gauss elimination, because in the LU decomposition, we just need to perform the forward elimination once, but the Gauss elimination need to perform the forward elimination many times. For example, if you have 3 input and 3 outputs, you need to perform at least 3 forward eliminations. So you must know that LU decomposition is an improvement and extension of the Gauss elimination in terms of efficiency. That means the LU decomposition can solve faster than the Gauss elimination, especially in multiple input, multiple output case. In terms of accuracy, both of them has the same accuracy. So for the LU decomposition, you have the AX equal to B. So A matrix, you need to perform the LU decomposition to obtain the L matrix and U matrix in the first step. In the second step, take the L matrix here and take your output to be on the right hand side, and you find the D matrix. Then you can substitute the D matrix here, and then by using UX equal to D, you can find the unknown X. So these are the important steps to solve the inverse problem by using the LU decomposition. So please make sure you know this. Lastly, we can use the LU decomposition to find the inverse matrix. So let's say we have the matrix A. We want to find the inverse matrix. By knowing A multiplied with inverse matrix is equal to identity matrix. When you compare this to this equation, then you are going to find your X, which is equal to your A minus 1, and then your B will be the identity matrix. If the size of A matrix is 4 times 4, then your identity will be 4 times 4 as well. So you have 4, 1 at the diagonal, and the rest will be 0. Then your inverse matrix will be 4 times 4 as well. Because when you multiply A with the inversion, so 4 times 4 here, 4 inner dimension here should be the same, then you obtain 4 times 4 to be the output. We can solve this problem by assuming the system is A. So this is the system matrix, and then for your output, let's say the B1 at the first column, so you have 1, 0, 0, 0. Then from this 1, 0, 0, we can obtain the solution for x1, which is the input at the first column. Then you can continue for your B2, B3, and B4. Okay, repeat the same procedure to find your x2, x3, and x4. Then you can get the rest, and this is the answer for the A inversion.